This topic focuses on scatter plots and the correlation coefficient. Over the course of the two videos, we're going to learn how to generate and interpret scatter plots, the correlation coefficient, and p-values for the correlation coefficient in Jamovi, as well as a few other things pertaining to this statistic. The first thing we're going to do is briefly review information about scatter plots and correlation that we covered in lecture. Scatter plots and correlation coefficients focus on statistical procedures that allow us to answer research questions about the relationship between two continuous variables. That is, does someone's score on one variable give us any information about what their score may be likely to be on another variable? And so for this example here, where I have a little scatter diagram showing the relationship between time it took on exam, so time it took a student to complete the exam, and the grade that student got on the exam. That's depicting a relationship between those variables. This scatter diagram is telling us something about the question of whether how long a student took on the exam is related to what grade that student got on the exam. Okay, so that's what we were talking about in terms of the relationship between two continuous variables. We learned in lecture how scatter diagrams can give us a visual of that relationship. When we inspect a scatter diagram, we can usually get information about the strength, or in other words, consistency of a relationship, the direction, and the pattern of a relationship. And if you are unclear about what those terms mean, then I suggest you just go back and take a peek at the notes from lecture. All right, so scatter diagrams give us a visual sense of what's going on. We can also calculate a correlation coefficient, which is a number that is calculated for a sample that tells us precisely what the direction and strength is of an association between these two variables, or between any two variables. We talked about how the correlation coefficient can be positive or negative. If the R value is positive, that means that we have a situation where high scores on X are going with high scores on Y, and low scores on X are going with low scores on Y. So this scatter diagram here depicts a positive association. And so if we were to calculate the R value for this sample of data, it would be positive. And so you can see that, high scores on X, so say time on exam is X, and grades is Y. So high scores on X, high time on exam, so more time to take the exam, go with high scores on Y. High scores on X go with high scores on Y. High time on exam goes with high score on grades, and then lower time to complete the exam also goes with lower scores on grades. Okay, so this is a positive association. Get a positive number for R. For a negative correlation, it's the inverse of a positive correlation. This is a situation where high scores on X go with low scores on Y, and then low scores on X go with high scores on Y. A negative association is depicted in this other scatter diagram. So the relationship between marital satisfaction, let's call that X, and overtime hours worked, let's call that Y. High scores on X, so high marital satisfaction, is associated with low scores on overtime hours, right? That's depicted like that. And then low scores on X, so low marital satisfaction, goes with high scores on overtime hours. Okay, so if we calculated the R value for this sample, it would be a negative number. R can range from -1 to +1 being a perfect positive relationship, -1 being a perfect negative relationship. And if R is around 0, it means there's really no relationship between X and Y. So someone's score on X doesn't tell you anything about what their score is likely to be on Y. This is a text taken directly from the lecture notes, just providing rough boundaries of how you would describe small, medium, and large correlations. So we would call a small correlation something, for a positive correlation, an R that fell between 0.10 and 0.29. A small negative correlation would be an R value between negative 0.10 to negative 0.29, etc. Right? These are just the verbal boundaries, or the boundaries of R that we use to verbally describe small, medium, or large correlations. Something that I also noted in lecture, though, that when you want to compare the relative strength of correlations, you're not actually using the R value, you're using R squared. We also talked about how the correlation coefficient can be used as a descriptive statistic, that is just with a sample of data where you want to describe the direction and strength of a relationship between two variables, but it's also possibly to test whether R is statistically significant. And that means you can test whether R in the population studied is significantly different from 0. So that's some background review on scatterplot and correlation coefficients. Hopefully it jogs your memory and got you all warmed up for what we're about to do next, which is generate and interpret scatterplots, R and p-values for R in Jamovi. Before we do that, we've just got to get set up with the materials that we're going to use for the example we will work with here. And this is all the reference information for the source of the data we're using. To access the data, we are going to have to load this module into Jamovi. Okay, let's pull up Jamovi here. So I think you've loaded modules before in this class. We're going to do it again. So you're going to go to Modules and Jamovi Library, and you're going to find the module called LSJ. So it's, for me, it's under installed because I already have it installed. But that's the module that you are looking for there. Okay, so you are going to install that, and when you install that, you'll be able to import the data that we need for this example we're going to use. So once LSJ is installed, then you're going to open the data set from this module. Okay, so this is a little bit different than how we have been opening data sets typically in these lab videos. So I'm going to walk you through it. Okay, so you're going to go to the regular menu button, but then you want to go to Open, and see, now you've got Data Library. So you're going to click on Data Library, and because the only library you have loaded is LSJ, or it might bring you up here actually. So click on Learning Statistics with Jamovi folder, and then, oh, got the wrong one. Right, we're not using that one. I accidentally clicked on it. All right, so we're clicking on the hamburger menu, open, and it will probably bring you up to this folder. Keeps doing that. I gotta click on it just one time. Open. All right. Anyhow, once you just click on it once, don't double click it, or else it'll put you in that doom loop that I was just in. And the data file that you're looking for is called parented. Okay, it is annoyingly not in alphabetical order here. So these are all data sets that you can download with this module. You know, you'd think it'd be in alphabetical order. It is not. You just have to look for the parenthood data set and go ahead, open that up. All right, so once you just have one data file open, sorry, that was a lot of file opening going on. Now I just have this one data file open, the parented data, and I'm going to explain this data set a little bit. And I've taken this quote from the Navarro and Foxcroft text. You can read through it. I'm going to just summarize it briefly. Essentially, this researcher created a fictitious data set based on real events, which I can confirm, having been a parent to young children for many years now. And it is a data set that is designed to answer the question of what is the relationship between how much a parent sleeps and how much a baby sleeps, and then also how much a parent sleeps in relation to how grumpy that parent is, and how much a baby sleeps in relation to also the grumpiness of that parent. So relationships between sleep and grumpiness, basically. This researcher collected data from 100 days of sleep in which she recorded a couple of things about that person's sleep and how much their baby slept. How much, so Dan is the parent, okay? Actually, the name is Danielle, and so it's the mom. So how much the mom slept, Dan sleep, and this was in hours per day. How much the baby slept, again, measured in hours. How grumpy Dan was. Make sure this is a continuous variable, okay? Otherwise, it's not going to do what we need it to do it if it's a nominal variable. So for some reason, when Jamovi opens this data set, it says that this variable is nominal, which it's not. It's just making a mistake. So those are the main variables that we're interested in. How much Dan slept, how much the baby slept, and then how grumpy Dan was the next day. And then the other two variables are variables that we're not going to use. This is the ID. This is basically the ID for the day, right? So this is day 1, this is day 2, this is day 3, etc. And it's exactly the same as the day variable. So I'm not sure why both are there, but anyhow, they are. You can delete them if you want. We are not going to use them. All right. So we're going to be looking at, like I said, some of the relationships between how much the parent's sleeping and how much the baby's sleeping, how much the baby's sleeping and how grumpy the parent is, that kind of stuff, right? So we're going to look at a couple of different correlations here. The first thing that we should do when we're working in Jamovi with this kind of data set is to just look at the basic descriptives of all the variables that we are going to be looking at, okay? And so this is what this information is all about, right? These are the variables that we're interested in. We're going to be looking at the correlations between those variables. So let's pull out some of the descriptives. So let's get the mean and standard deviation for our variables here, our continuous variables. So we're going to do what we already know how to do. Get mean and standard deviation, analyses, exploration, descriptives. We are going to put Dan sleep, baby sleep, and Dan grump in the window there. We can ask for the histogram as well. All right. So again, just want to get a sense of what is going on in the data set. Dan sleep. You can see Dan is sleeping an average of 6.97 hours per night. That's probably not enough. The baby is sleeping a little bit more, on average 8.05 hours per night. And Dan is rating her grumpiness on an average of 63.7 points on that 0 to 100 grumpiness scale. All right, so let's just kind of take a peek. This distribution of Dan sleep looks kind of normal-ish. You can always throw a density plot in there to get a smooth line. Yeah, so that looks pretty good. Baby sleep, that looks pretty good. Dan grump. So we don't have anything too weird going on in terms of the shapes of our distributions. And we can just do that as a preliminary step to investigating our correlations. It's good to have a descriptive sense of what's going on with our variables. Okay, so now we're going to start looking at some relationships. All right, so if we have 3 variables in our data set, we can actually look at 3 different correlations, right? We can look at the correlation between, Dan's sleep and how grumpy Dan is. We could also look at which is what we're going to do first, but we can also look at the correlation between how much Dan sleeps and how much the baby sleeps. and the correlation between how much the baby sleeps and how grumpy Dan is, right? So we can look at three correlation coefficients, three associations based on this data set, but we're going to start with one. So we're going to start with looking at the relationship between Dan sleep and Dan grump. So let's follow along in Jamovi. Here we go. So we're going to analyses, regression, and correlation matrix. We're going to move Dan sleep and Dan grump into the right-hand window there. Right, and we are going to leave everything as is, except we're also going to ask Jamovi to plot correlation matrix. Okay, that's all we need. Okay, so here we are given a table called the correlation matrix and a plot, which is our scatter plot. So you can see this is the output that we're given. And I'm going to flip back to the handout here because I've just pasted that output into the handout. It's just easier to see in this version with my annotations added. So here I just want to point out for you where to find some things and kind of what to look at, how to interpret this. It's not that much information that you're given, right? It's kind of nice in comparison to some of the output we've been looking at lately. This is pretty simple in comparison. You just get one table and one picture. And so let's first look at the scatter plot. Okay, so this is the scatter plot here, and we can interpret it just the way we would any scatter plot. This is a fairly obvious scatter plot interpretation with kind of made up data. You often see this. You don't get such a nice obvious pattern with real data sometimes, but for here it's great. Basically, the scatter plot shows you that the relationship is clearly negative, right? The relationship between Dan sleep and Dan grump is negative, right? The more sleep Dan gets, the less grumpy she is. And you can also see that the dots fall fairly close along the line. They're fairly tightly clustered there. And so it appears to be a fairly strong relationship, a strong negative relationship. The next thing to look at is the correlation coefficient. Remember, the correlation coefficient kind of translates our reading of the scatter plot into a number that in one punch gives us the direction and strength of a linear association. So where is the correlation coefficient? It's a little hard to see. I'm going to zoom in here. Okay. So here Pearson's R. Remember Pearson R, he was a pirate. This is our Pearson's R. This is the correlation for the relationship between how grumpy Dan is and how much sleep Dan gets. In keeping with our interpretation of the scatter plot, we see this as a strong negative association, right? So pretty consistently, the more sleep Dan gets, the less grumpy she reports being the next day. So that's the correlation coefficient. Okay, the final number we're going to interpret in this output is the p-value. Remember that we have a p-value for the correlation coefficient. The correlation coefficient is our sample score, and as has been the case for other tests, it has a p-value tied to it. So, and also as was the case in previous topics we've covered, we will still just need to consider the significance level and then compare the p-value with our significance level. Unless otherwise indicated, which it wasn't in this example in the textbook, kind of they didn't indicate what the significance level is specifically, and in that case we just assume the significance level is 0.05. So we're assuming the significance level is 0.05. We look at our p-value, right, which is less than 0.001, so that is obviously also less than 0.05, and so we say that the correlation of negative 0.903 is significant. Right, so it's significantly different from 0. There is a correlation in the population, or there very likely is. All right, so that's all of the output, right? The scatter plot, the R, and the p-value for R. The final thing we're going to do with this is just to consider how to interpret it all and communicate this finding in writing. And so if I was, trying to communicate the meaning of this output to an audience, you'd probably say something like this. So the correlation between how long Dan sleeps and how grumpy Dan is you just report the correlation and the p-value, and you say that's a strong negative relationship and was statistically significant. Therefore, when Dan sleeps longer, he's less grumpy. Now, you might, the wording could be slightly different, but all of those key elements are there, right? You're reporting R, you're reporting the p-value, reporting the strength and direction of the relationship and that it was statistically significant, and then also just translating that into kind of common language that anyone could understand. And that's the last part there. All right. So I also want to show you just this is kind of the meat of it. This is what I want you to kind of mostly remember about this, but I want to show you just a couple other things. So I want to show you that you can add variables to the correlation matrix so you can examine multiple relationships simultaneously. So you don't just have to be contained or be constrained to looking at one correlation. You can put multiple variables in, or more than two variables in to get a correlation matrix that gives you, 2, 3, 4, however many you want correlations. And so let's do that for our example here. If we click back on the correlation coefficient, let's put our last variable here, baby sleep, into our correlation and see what you get. Now you have correlations for 3 relationships, okay, and also accompanying p-values for those correlation coefficients. So again, you can see that this is the output that Jamovi generates, and I'm going to flip back to the handout. Okay, and so you can see that, we still have the original 2 variables that we put in the correlation matrix. The relationship between Dan sleep and Dan grump is negative 0.903, and this is the p-value, right, less than 0.001. Now, right below this, we have the correlation between Dan sleep and baby sleep. Okay, so this is the correlation between how long Dan sleeps and how long the baby sleeps, and the p-value for that correlation. And then finally, we have the correlation and its p-value for the relationship between how grumpy Dan is and how long the baby sleeps. Okay, and then we have corresponding scatter plots for each of those associations. And you can kind of read it. It's a little bit hard to read because the variable names are way up here, but you can figure it out, right? Like this is here the correlation between how long Dan sleeps and how grumpy Dan is. This quadrant here is the correlation between how long Dan sleeps and how long the baby sleeps, right? And then this quadrant here is the scatter plot for the correlation between how long the baby sleeps and how grumpy Dan is. Okay, so it's a little bit confusing, but I'm sure you can figure it out. You're smart individuals. All right, so now I want to interpret these new relationships that this output tells us about, right? So remember in our first attempt at generating a correlation matrix, we just had this first relationship, but now we have 2 more. So let's interpret these new correlations that have been produced. So Dan grump and baby sleep. All right, let's try to see some of this a little easier. All right, so Dan grump and baby sleep. Let's find this information on the correlation matrix. There we go, Dan grump and baby sleep. It's right here. So the correlation between how long the baby sleeps and how grumpy Dan is an R value of, I forgot it already, negative 0.57. And then we put the p-value in as less than 0.001. Right, and this is so it says negative relationship, so what I'm looking for here I'm looking for the strength. So this is a strong negative relationship. How did I get that? We have to go back and refer to this table here, right? Or the large relationship. I guess you could say strong or large would be fine. I'm gonna go back and change it to make sure I say large, and I'm more precise with that language based on the chart. So it's a large negative correlation. All right, so I'm just going to change that to large, and then I should also probably go and change this. Okay, so I'm going to say this is a large negative relationship just to be very consistent with the chart that I gave you, which is a large negative relationship. Okay. So now the last part is just putting it in words that anyone can understand. We would say, therefore, when the baby sleeps longer, Dan is less grumpy. All right, so that's the relationship between Dan sleep and baby sleep. And now let's look at the relationship between Dan sleep and baby sleep. So is how long Dan sleeps related to how long the baby sleeps? Baby sleep, Dan sleep, so 0.628. Let's do this, equals 6.3, and p-value is less than 0.001. Again, right, I'm just getting that information from up here. Right, so that is a large positive relationship and is statistically significant. Therefore, when the baby sleeps more, Dan sleeps more. And I can confirm that that is a true, probably a true statement. Okay, there we go. All right, one thing I do want to cover here is this issue. You may be wondering if, what if the correlation was between, say, negative 0.10 and positive 0.10? This is like a very small, negligible association or no association. In this case, if the correlation was not significant, which is going to be the case most of the time when you have this tiny of an association, the p-value is going to be greater than 0.05. What you would do would be report R and the p-value as usual, but you don't need to report its strength or direction. You could just say, therefore, there was no association between the variables. Sometimes, however, when you have a very large n, it can be true that a correlation between, in that negligible region, like negative 0.09, positive 0.05, it actually can be significant. And this is because when you have a supercharged n, you have very high statistical power. So you have the power to detect a real but tiny association. And in this case, you would report the R and the p-value as usual. Okay. Then for the interpretation, if you have a positive tiny relation, you would report something like a negligible but significant positive correlation was found between the variables, meaning that people who scored high on whatever X was were only very slightly more likely to score high on whatever variable Y was. And then the same thing, only the wording would be a little different if you have an R value that's negative. But again, this is only for the case when you've got these tiny R values with a significant p-value. Okay, so when their p-value is less than 0.05. All right. If we wanted to interpret the relative strength of the correlations, we would want to use R squared. Okay, so if we were comparing, the strength of the relationship between how sleepy Dan is and how grumpy Dan is, and say how much sleep Dan got and how grumpy Dan is, and say how much sleep the baby got and how grumpy Dan is, then we would use R squared. Okay, so let's actually, it seems to me to make more sense. Say we might want to compare the association between how much Dan sleeps herself and how grumpy she is, and then how much the baby sleeps and how grumpy Dan is. So I don't know, that would seem to make sense. That might be something we were interested in comparing. So let's go and do that. All right, so I just calculated those R squared values. I just literally squared R for each. And just a reminder, that if we were comparing these associations, we would say that, the R squared for this association was 0.32, the R squared for this association was 0.81, and so you'd be able to figure out that that means that, so indeed, there's a stronger relationship between, sorry, I just changed those around because I had the wrong R written here, but all right, so for the relationship between how long Dan sleeps and how grumpy Dan is, that is an R squared value of 0.81, and that's what you would compare with the relationship between how long the baby sleeps and how grumpy Dan is, and that's 0.32. So if you were to calculate, how many times larger this relationship is than this relationship, it would actually be 2.5 times, and you would calculate that based on the R square and not on the R values. So it would say, the relation between how much sleep Dan gets and how grumpy she is about 2.5 times stronger than relation between how much sleep Dan's baby gets and how grumpy she is. Right? And that makes sense. How long Dan sleeps should be more directly or more strongly or more consistently associated with how grumpy Dan is than, the relationship between how much sleep the baby gets and how grumpy Dan is, because maybe sometimes Dan's husband is getting up in the night with the baby, and so there's not going to be as direct a relationship with how grumpy Dan is when you consider the baby sleep versus how long Dan herself is sleeping. Okay, so what are all the possible directions of causality for these associations? Just in the interest of time, let's do just the association between Dan sleep and Dan grump. Okay, so it is possible, the first direction of causality is that how much sleep Dan gets causes grumpiness. Okay? Or say the more sleep causes less grumpiness. Okay? We can actually eliminate the other direction of causality. We can't say that how grumpy Dan is on one day causes how much sleep she gets the night before, because the sleep happens first and then the grumpiness happens. So we know that that's not a possible direction of causality just because of the way that the data was collected there. But a third variable is also possible, right? So it is possible that a third variable is causing, changes in both sleep and grumpiness. For example, you could probably think of a lot of examples. If Dan is busy or stressed at work, that might cause Dan to get less sleep one night and to be more grumpy the next day. Okay, so when you're interpreting correlations, you always want to be considering the different possibilities in terms of direction of causality. Right? We talked about that in lecture, and it's just kind of part of interpreting these statistics. So I wanted to touch on that here as well. Okay, and this is my last note on this video. I apologize for how long this has gotten, but I just wanted to talk about a note regarding scatter plots that's unrelated to the parenthood data set. And what I wanted to show you was that you can actually add unlimited variables to the correlation matrix. So, we started off with 1, and then we added 2 more variables, so we had 3 variables. And you could actually enter like 4, 5, 6, 7, 8, many variables in your correlation matrix, and you can get a ton of correlation coefficients. And I wanted to show you a trick to help draw your eyes to significantly correlations, which are usually larger correlations. And this is to check flag significant correlations. So say this is just another data set. I'm not going to have you open it, but it's got, multiple variables. These are personality traits. And if we put all of those personality traits into the window, we want to look at the correlation between all of these personality traits. If we click flag significant correlations, what Jamovi is going to do is going to put a little star beside each significant correlation, just like it did in the APA style table that we looked at in lecture. And kind of the beauty of that is that if you have a table that has a ton of relationships like this one, like 21 relationships, then your eyes are quickly drawn to the significant correlations and makes it easier to get a sense of where are those significant associations in this large set of correlations. So if you're ever in a situation where you have lots of correlations in a matrix, make sure you click that flag significant correlation button. And that's all for video 1.